Hola, buenas tardes. Mi nombre es Peter Godart y soy investigador postdoctoral at MIT. Just thought I would translate what he said in English into Spanish. That's actually the extent of my Spanish, so I'm going to switch to English right now. I'm sorry to get your hopes up. For the English speakers, again, I'm Peter Godart, postdoc at MIT. And I'd like to talk to you about sort of the other end of the spectrum, and that's sort of how do we address the problems that climate change has already caused. And so the previous speakers did such a wonderful job outlaying the process, the problems, and how things stand to get much worse. And indeed, when we talk about climate change, most of it is in terms of future projections. So we're thinking about how the behaviors of humanity in the past and in present day will affect the future of humanity. And this is pervasive in how we talk about solutions to climate change as well. We're constantly looking at different pathways for how can we not make this problem any worse. And all of the technologies that we think about, solar, wind, battery electric vehicles, grid storage, carbon-free aviation, all of these sort of think about the future of the planet. But as we stand here in 2022, it's difficult to look at the world and ignore the fact that the climate has already changed. We're already at plus 1 degrees Celsius warming, and alone this has caused an increase in wildfires, droughts, natural disasters, all of which are becoming both more potent and more prevalent as a result of the climate that's already changed. And we have this parallel issue that industrialization and commercialization has caused a waste problem as well. And these problems are compounded by natural disasters, which themselves generate quite a bit of waste. And what we're seeing is that around the world, is those communities that are more susceptible to the effects of climate change currently are also the ones who have to deal with this waste. And so this is very much a social justice issue, a humanitarian aid issue as well. And so this picture right here actually is what inspires the majority of my research, which is how can we solve some of these problems simultaneously? Is there something we can do to transform this waste, which itself, again, is a problem, into critical resources that people need? Electricity, potable water. So in this talk, I'm going to talk about my research, which is turning aluminum into a water-reactive fuel for producing hydrogen at very high energy densities and very rapidly. I'll talk about how we actually make aluminum water-reactive to produce hydrogen using a recoverable gallium-indium catalyst. I'm going to talk about how we turn practical scrap aluminum, so actual aluminum waste, into this water-reactive fuel. I will talk about how we can generate electricity and potable water using this fuel, some of the commercialization opportunities looking ahead in the next couple years for this fuel and what the long-term vision might be. And I'll also talk about some other sources of waste as hydrogen storage as well. So before getting into that, I just wanted to give a brief background. So I've always been inspired by this idea that resource constraints breed innovation. In high school, I was involved in this competition in New Jersey, where I'm from, put on by Panasonic, and we were tasked with solving these very complex engineering problems using waste, literal waste. They would give us a couple DC motors, but aside from that, you see this is a tank made out of packing peanuts on the treads. Those are wire spools as wheels, and the rest is basically popsicle sticks. And actually, this challenge here was develop a robot that could put out a wildfire. It's kind of a fake scenario. So I've also been very interested in this problem, and the climate change problem as well. I also did some research when I was in high school at Rutgers University, looking at how we can use functionalized silica to do carbon capture and storage. Didn't pan out, but it was an interesting study in looking at how we can turn the second most abundant element on Earth into something useful for carbon capture. After I did my undergrad, I went and worked at the NASA Jet Propulsion Lab, where we're developing and sending robots to Mars, which is arguably one of the most resource-constrained environments that we have access to. That had a lot of challenges. And also while I was there, I had this opportunity to work on a power system for a lander that might one day go to Europa, which is an icy moon of Jupiter. And the idea here was to take some of the vestigial components of this lander, the components that are no longer needed, landing gear, heat shield, make them out of aluminum, and then react that aluminum with the ice that's already present on Europa and generate hydrogen to supply robots that way. And it was while I was there, and I was part of the team that drove around the Curiosity Mars rover, and that experience coupled with this experience, I sort of had this epiphany that I'd much rather be spending my time working on problems that we face on this planet, and I saw a way that we can actually apply some of these technologies to the issues of climate change specifically. So I went back to graduate school at MIT and developed the work that I'm going to present to you here today. So just taking a step back and thinking about Earth's energy resource constraints, essentially the most abundant renewable source we have is solar energy that's easily accessible. And in some ways, we essentially are converting this solar energy into all of the fuels and the electricity that we use today, whether it be fossil fuels, which originally began as sunlight through photosynthesis, turning into coal and dinosaur juice, the remains of dinosaurs that ate plants. We have solar, photovoltaic, we have wind energy, which is arguably powered by the sun as well, and hydroelectricity, which also can be, which is powered by the sun as well, the water cycle. Now we have a very important imposed constraint, which is that we can't emit carbon dioxide anymore. So we're trying our best to eliminate this source of energy, or this fuel. But there are some other sort of hidden constraints with some of the other renewable sources as well, as some of the other speakers touched on. And those are resource constraints in terms of specific metals and some rare earth elements that go into converting sunlight, these renewable sources, these downstream renewable sources, to electricity that we can then use. For example, cobalt is one in particular that people are worried about running out very soon. And in fact, many critical element reserves are actually on track to run out this century, which poses a very significant problem for humanity. And then there are other constraints, which are that local energy supply can also be disrupted by disruptions to infrastructure. And this is particularly an issue for disaster relief and for electricity grids in the aftermath of a natural disaster. But fortunately, there's this other significant untapped energy resource that people are often overlooking, and it's sitting in landfills across the world. And so we can look at the energy density of many of these materials that we think of as waste. Compared to diesel, they're quite competitive in terms of mass. And I'm going to start by focusing in on this aluminum water technology first. So this research in particular is inspired by the idea that aluminum is abundant, cheap, and highly energy dense. Again, it's comparable in terms of energy density per mass, gravimetric energy density, joules per kilogram, but where it really excels is in the volumetric energy density. It actually has double the volumetric energy density of liquid hydrocarbons. And the way we extract this energy is by, as we do with all of these other sources on here, is we oxidize it. And we can oxidize it with water by this reaction here that produces hydrogen, this inert and valuable aluminum oxyhydroxide, which I'll talk about later, and heat directly. And the embodied energy in that aluminum is released in roughly equal proportions between the heating value of the hydrogen that's produced and heat directly. And currently, one of the reasons that aluminum is ending up in landfills all over the world is that we're currently limited in terms of our aluminum recycling to easily identifiable aluminum alloys. It's very easy to say, a can is comprised of certain alloys, so if we have cans, we can recycle those very well. But if we're shredding a car is made up of many different types of aluminum, and you can't simply combine the different alloys because the mechanical properties will change drastically. And so currently it's very expensive and difficult to separate out aluminum by those different alloys. And so as a result, we're recycling less than half of the aluminum that goes out into the world. And this is resulting in millions of tons of aluminum accumulating in landfills every year. And I thought I would address this early, and so aluminum happens to be the most abundant element on the Earth, but it's not a great fuel source because it's found in nature as aluminum oxide. And of course, the reason aluminum is so energy dense is that we had to put that energy in there to begin with to reduce it and pop that oxygen off the aluminum oxide. So it's a very energy intensive process, so it's more of an energy storage method than a fuel. And the other main problem, which is why this is currently not being used as a large-scale energy storage system, is that we can't simply mine aluminum and turn that into, we can't mine aluminum ore and turn that into pure aluminum easily, because we're generating a significant amount of carbon dioxide in the process. And actually, currently, the aluminum industry is responsible for about 2% of global carbon emissions. So that's substantial. We'd have to address that problem in order to look at aluminum as sort of this global energy storage, but I'll get into that a little bit later. So going back to this aluminum-water reaction, we can basically think of aluminum as hydrogen storage. Instead of shipping hydrogen, we might ship aluminum and then react it with water on site to generate hydrogen by this reaction here. And so we can compare the effective storage density and specific energy and energy density of this aluminum water system to conventional means of storing hydrogen. And so if we think about storing hydrogen as a gas, the state-of-the-art way to do that is putting it in a tank at about 700 bar. And if we do that, we can achieve a weight percent of 5.4%. So that means 5.4% of the total mass of the storage system is hydrogen. That goes up substantially for liquid hydrogen. Aluminum, I'll address your attention to the bottom line here, the one in purple, where that's if we ship the aluminum and then we use water that we have on site. We can actually achieve a weight percent of 11.1. That's double that of gaseous hydrogen. But where this is very attractive is all the way on the other end, where we have a volumetric energy density of just the hydrogen that's produced of 36.3 megajoules per liter, which is 5 times greater than that of liquid hydrogen. So this is one of the most energy-dense ways in terms of volume to ship and store hydrogen. Not only that, this also eliminates a number of the safety concerns associated with gaseous and liquid storage. And all of this is ignoring the heat that's released in this aluminum-water reaction as well. It's a highly exothermic reaction, and there's lots of things you can do with that heat as well to generate additional value. And finally, this aluminum oxyhydroxide byproduct is itself very valuable and can be sold to offset operating costs, but actually can be sold for a profit, or can be re-smelted back into pure aluminum and avoid some of the carbon emissions associated with mining the bauxite ore. So how do we actually make aluminum water reactive? So aluminum will spontaneously react with water to do this reaction, but all aluminum that's been exposed to oxygen will have a very strong and robust oxide layer on the outside. And it's that oxide layer that is preventing, for example, my MacBook from spontaneously reacting with water. And so the key here is to figure out how to disrupt that oxide layer just in time for that aluminum water reaction to happen. And it's been known for a very long time, a couple decades, that if you dope the aluminum grain boundaries with a liquid metal alloy, so in our case, we're using a liquid gallium indium eutectic alloy. If you apply that to the surface, it'll diffuse into the grain boundaries of the aluminum and will disrupt that oxide layer at the surface and allow hydrogen to be developed. And using this process, we're using less than 5 weight percent gallium and indium, but we're getting greater than 95% theoretical hydrogen yields. And you can see here that's a microscopic video of aluminum grain boundaries from which hydrogen is evolving. So we had known that we can do this, and here's a little video that shows just how effective this is. This is sped up, but you can see just how exothermic this reaction is. Immediately you're seeing hydrogen bubbles, but now you're actually seeing the water that's in this cup boiling off. But there were a number of questions that prevented this from being a practical energy storage method. We simply did not know how this gallium and indium facilitated this aluminum water reaction. We didn't know what actually happened to the gallium and indium itself. And very, very importantly, no one actually knew how to recover and recycle the gallium and indium. I spent a minute or so at the beginning of this talk talking about resource constraints, and here we are suggesting that we use gallium and indium and throw that in the trash. That simply does not work. So during my PhD, which I completed last year, I set out to study this and figure out how can we solve some of these problems. I discovered a new method for studying this aluminum water reaction. I could actually get these aluminum pellets that were treated with the gallium and indium to spontaneously disintegrate and react with water vapor. And what this allowed me to do was sort of pause the reaction at various stages and then use standard materials characterization techniques like scanning electron microscopy and X-ray diffraction to really figure out what's actually going on in this reaction. And what I discovered is that, if we do this gallium and indium treatment, apply water vapor in this case, or even liquid water, and then immediately stop the reaction, we see that what's happening is that the aluminum is disintegrating along the microstructure. And it does so in this fractal-like exfoliation process that is self-similar all the way down to the nanoscale, as you can see on the right image over there. Not only that, depending on the stress state of the aluminum that we input into this process, there's all these other secondary dynamic effects, like grain ejection, which had never been observed before, where you have this asymmetrical walking of the aluminum grains out of the surface in a very dynamic, very fast process. And this is also mirrored at the macro scale. So here is a 6 millimeter aluminum ball bearing, very pure aluminum ball bearing, that's been treated with the gallium and indium. I apply a drop of water onto it. This is in real time. You can see immediately hydrogen's being generated. And because of the heat, we have all these interesting secondary thermal processes. You'll see this popcorning effect happen. And as we zoom in, we'll see that what's happening in addition to the aluminum turning to aluminum hydroxide, you're simultaneously getting this disintegration of the aluminum. And actually, primarily what you're seeing here is pure aluminum that's been disintegrated. There's not enough water present to fully react it with the water, fully react the aluminum and the water to produce hydrogen. This is the last clip. And so what this is all doing is it's effectively opening up the surface area of that aluminum to the further oxidation by water. And I'll talk a little bit more about that in a minute. But going back to this main problem of how do we recover the gallium and indium. Again, gallium and indium are very expensive. At this eutectic mixture, it's about $350 per kilogram. So if we were throwing that away, we'd essentially be generating hydrogen at $18 per kilogram of aluminum. Which is not great, and that equates to $174 per kilogram of hydrogen. The DOE hydrogen target is about $2.30. You can do it with methane reforming for about $1 per kilogram of hydrogen. So this is just simply not sustainable. Not only that, we're just dumping gallium and indium down the drain, which is also not good. And again, as I mentioned previously, no one knew how to do this recovery. And you can't simply recover it by mechanical means. And people thought maybe you could centrifuge it and it would sort of fall out. But we, of course, tried that, and we were not able to do that. So we had to dig a little bit deeper. And so what I ended up doing was coming up with a model for this aluminum water reaction. And informed by the videos and the SEM images that I showed you, we realized that this aluminum water reaction is happening in two parts. First, the aluminum is disintegrating along those grain boundaries, and that's the result of some initial reaction that's happening in the liquid metal intergranular phase. And then now you have all this surface area that's exposed, and there's no oxide layer on those internal surfaces of the bulk aluminum, so the aluminum water reaction can proceed uninhibited from there. And what we're seeing as well is that this confirmed the fact that in normal conditions, the gallium was also being oxidized, which explained why we were not able to recover it. The gallium turns to gallium hydroxide or gallium oxyhydroxide, and we're left with solid indium spheres, as you can see from this energy dispersive spectroscopy image here. Both of which are very difficult to separate out from that aluminum, would require a significant amount of energy. Oop, that closed on me. Let's restart that. And so using this model, we realized that the new challenge was to figure out a way to selectively passivate that gallium water reaction, but allow the aluminum water reaction to proceed. And I discovered a method to do this by modulating just the ionic strength of the solution and controlling a few other factors, like the rate of crystallization of the aluminum hydroxide. But discovered that by doing so, and in this case I'm just using sodium chloride, by doing this, as you can see, the aluminum disintegrated. This is a time-lapse video. It's generating hydrogen. you can see these liquid metal beads literally floating to the surface. And what's fascinating here is that these little liquid metal beads, which are the gallium and indium, have a small amount of aluminum dissolved into them, and so they're still generating hydrogen. And because of some what are called Marangoni flow effects, these liquid metal beads are actually buoyant in the reaction product, and they literally float to the surface. And despite that, they're also much higher density than the surrounding materials, so it's very easy to separate out, and it's recoverable as a liquid, which is very important. And so in the lab, just using the sodium chloride, we were able to recover greater than 99% of the gallium and indium that we put into the system as a liquid. We recovered it back out as a very easily separable liquid. And what's very cool about this is that it also works all the way down to sodium chloride concentrations at seawater levels. So this is a process that is scalable and possible to do with just seawater. So moving on from there, I took this technology and wanted to apply it to actual practical scrap aluminum. So we knew that this worked with our 99.999% pure aluminum ball bearings, but how did this fare when we threw in other contaminants, particularly surface contaminants like paint on the surface of a soda can, for example? And we wanted to do this without having to remove the paint specifically. And so we chose soda cans as a very difficult case study for converting aluminum scrap. And we developed this process for very simply just shredding the aluminum. This is actually a paper shredder that's been slightly modified. We compact these shreds into pellets and then do this surface treatment of the gallium and indium. We showed that there are a number of interesting parameters affect the reactivity of these scrap pellets, including the geometry of the chips that go into the pellets, and also importantly, the total strain energy and compaction pressure used to make those pellets. But the net result is in the top right corner here. You can see that under the right conditions, we can actually produce fuel that is, one, very consistent in terms of its hydrogen output, but also achieves a very high hydrogen output at almost 97%, which is actually higher than the pure aluminum that we were using before. I then went ahead and measured the energy inputs to this process and showed that even very conservative, very inefficient lab setting, we can still do this treatment process for less than 2% of the energy that we get back out from the aluminum. And again, that's because all of that energy that's embodied in the aluminum went in during the reduction process. And here we're just manipulating the aluminum in a pretty superficial way, actually, to make it water reactive. In this process, the paint on the outside of the used beverage cans can be easily removed. It's not oxidized or damaged during the reaction process. What's interesting here is that these used beverage cans actually have a polymer coating on the outside and the inside, and essentially what we're doing is reacting the aluminum from in between those polymer coatings. And you can actually read the labels off these paint shreds that come out of our process. So we've figured out how to develop this fuel. We figured out how to recover the gallium and indium. We also wanted to see what are some of the practical things we can do with this fuel. Can we generate hydrogen at high enough flow rates to do anything useful? And the answer is yes. So this is actually one of the projects that sort of kickstarted everything. And like Professor White was talking about, this was also fueled by student innovation. There's a capstone mechanical engineering design class that I took as an undergrad at MIT and then was an instructor for, co-taught by Professor Douglas Hart. And one of the final projects for this class, when I took the class, was to generate an emergency power supply at the 3 kilowatt level that utilized this fuel. And we were able to do just that. We were achieving flow rates of 39 standard liters per minute. It's a very simple system. It's in the top right here where we have a batch reaction chamber. We input aluminum and water. We control the pressure in that reaction chamber to be just a little bit above atmospheric pressure. We dump in excess water to cool the reactor and then condense that water out and send the hydrogen to a PEM fuel cell. It's very easy to control this reaction because all of that surface area that opens up when you start the reaction, the aluminum disintegrates, means that the reaction dynamics are very fast So it responds almost immediately to small changes in water flow rate into the reactor. So it's very easy to control. We were just using a simple proportional derivative controller for this. A couple years later, we then scaled this up to the 10 kilowatt electric level, and we effectively scaled this up and shoved it in the back of a BMW i3 electric vehicle. And we were able to drive this vehicle around by generating hydrogen that would charge the onboard batteries. And in this case, we were generating about 120 standard liters per minute. Worked very well as well. In both of those applications, we were effectively dumping the heat because a PM fuel cell needs to operate at room temperature, 20 degrees Celsius or so. So we were cooling down that hydrogen and using water to do that. So I was very interested in figuring out other ways to utilize that heat. And for my master's thesis, I worked on a project for using that heat to do potable water generation via desalination. And what I came up with is a system that effectively it's a giant piston, where on one side of the piston, we're doing this aluminum water reaction. That generates high pressures, which is able to pressurize seawater against a semi-permeable membrane and do reverse osmosis desalination. And it turns out, it's basically a big heat pump, big heat engine, and it's able to do desalination about 40 times more efficiently than just single-stage evaporation, just boiling off the water. We have a couple patents on this, actually, and we've shown that, this is a bit of an aside, this can also be used very well for other metal-water reactions, like sodium-water reactions, and also is compatible with solar thermal energy and even industrial waste heat. And this is, again, for more small-scale desalination on sort of the family-size scale. And what's interesting about this is that the hydrogen is not consumed in this process, so we're just using that thermal energy to do mechanical work, and then we have all of that hydrogen left over to send through a fuel cell or an internal combustion engine to do other things with. Here's a video of it in action. And so it requires about 20 grams of aluminum, which is about a soda can and a half worth of aluminum, in terms of mass of an empty soda can. And that can desalinate, that has enough energy to desalinate a liter of seawater at 3.5% salinity. And that's pure water coming out of there. So looking ahead a little bit and thinking about what's next for this technology, well, we're in the process of commercializing it. And our idea for the initial commercialization pathway is to develop a municipal scale aluminum waste processing plant where we're taking in aluminum and water, doing this treatment process, turning that into water reactive fuel that we either ship or convert the hydrogen directly on site, recover that gallium and indium, put it back into the treatment process, and on the output, either send out electricity directly or send out aluminum hydroxide or oxyhydroxide or heat directly. And so the idea here is essentially we're an aluminum oxyhydroxide plant, which itself is very profitable. The heat and the hydrogen can be used to supplement municipal electricity generation or district heating, help offset carbon emissions there. Because this is an alloy agnostic process, this allows us to tackle that aluminum that is very difficult to recycle, sort of bottom of the barrel aluminum, which is either being shipped to other countries or just being thrown away. And preliminary economics show that for a pretty conservative aluminum cost and aluminum hydroxide resale cost, we can actually produce hydrogen at a net profit. There's a negative cost to producing hydrogen. So we can actually make $6 for every kilogram of hydrogen we produce. And then, of course, we can sell that hydrogen. And that amounts to being roughly 66 cents per kilogram of hydrogen before we sell the heat and the hydrogen. This is sort of the low-hanging fruit in terms of commercialization, but ultimately where I would like this technology to go is to ultimately start using aluminum as a way of transporting hydrogen in a very highly energy-dense way. Again, it's 5 times more volumetrically energy-dense than liquid hydrogen. We can use hydrogen as well to power emergency backup generators. And I'll talk about this in just a minute, but in the future, far future, this could also be a way to store renewable energy as well. So we did a simple case study and looked at a couple different countries and compared the scrap price to some conservative estimates for the profit that could be made by selling the aluminum oxyhydroxide, the heat, and the hydrogen, possibly converting those as well to potable water and selling those at utility rates. And what we see in that, in all cases, no matter where we look, we can generate several times the value of the input scrap aluminum itself. And that's the average scrap aluminum price. So tying this all together, the future of aluminum waste management could be that we use this aluminum activation technology to help close the loop. We can take aluminum at the end of its life cycle, turn it into aluminum hydroxide, extract that energy back out, and then put that aluminum hydroxide back into the smelting industry where we turn it back into primary aluminum. This improves the life cycle efficiency of aluminum and helps to reduce emissions associated with mining. That's today. It would also incentivize recycling and remove some of those current barriers. And this is all possible due to that gallium indium recovery. So you'd need just a small amount of this gallium and indium to begin with, and then this is a closed cycle from there. That's just taking in aluminum and water. This also gives us a way of dealing with energy from debris for climate change adaptation. So now we can make communities more resilient to climate change by giving them a means of turning their debris from natural disasters into a highly energy-dense fuel source to generate electricity and potable water. Over the next 10 years, there are a number of companies that are looking into doing carbon-free aluminum smelting. And I'm very excited about that because that unlocks an entirely different world of possibilities for this aluminum technology. Once we can reduce aluminum from aluminum oxide without those associated carbon emissions, and there's a major joint venture between Rio Tinto and Alcoa, the major North American aluminum smelters, that's doing this right now. This now allows us to think about aluminum as a way of storing energy from renewables for a very long time in a very stable way. We might even think about using aluminum then to start replacing single-use plastics and reducing our plastic waste and knowing full well that we can recover that energy from that aluminum that we're continuing to use more of. And then also, we might actually begin to think about jumping into those more difficult to decarbonize sectors that Howard was talking about, particularly aviation and long-haul trucking, and using aluminum to effectively store hydrogen. And I'd like to leave you with this other observation that aluminum is not the only hydrogen dense material in our landfills. Aluminum, again, is about 10 to 13 weight percent. But plastic, and polyethylene in particular, has a hydrogen density of 14 weight percent, and biomass has a hydrogen density of 12 weight percent. And there's some very interesting research going on using some machine learning techniques to develop catalysts for doing this effective pyrolysis type processes where you're separating out the hydrogen from these different materials and leaving behind solid carbon. And so if we look at sort of the global hydrogen demand, which is about 75 megatons per year, if we look at all of the aluminum waste that's currently landfilled, that's about 20 megatons per year, or about 2 megatons of hydrogen per year. So it's a very small percentage of the global hydrogen demand. But if we can start tapping into some of these other waste streams like plastic, we can start developing, plastic alone would account for about 40 megatons of hydrogen per year, which is more than half of the global hydrogen demand. So I would say that this fact alone indicates to me that looking at generating hydrogen from plastic warrants more research going forward. So I will leave you with that, and if there's time, I'll take a couple questions. Thank you.